Okay, Assalamualaikum. So this time I will do a problem on the isothermal process for an ideal gas. The ideal gas this time also air. So let's see the question first. A piston cylinder device initially contains 0.4 meter cube of air at 100 kPa and 80 degrees Celsius. The air is now compressed to 0.1 meter cube in such a way that the temperature inside the cylinder remains constant. Determine work done during this process. So this time also it asks for the work done. First, you highlight the important thing here, a piston cylinder device. So we assume that this is represent a process piston cylinder device. Okay, so it does not mention about frictionless whatsoever. Okay, so we just assume this is our system. Okay, air inside this initially contains 0.4 meter cube of air. So this is our system air, and also we highlight the important part here, 0.4 meter cube as its volume, 100 kPa and also 80 degrees Celsius. Okay, so this is all of the properties. The air is now compressed, so this is your typical process. Okay, compression. So it causes the volume to change into 0.1 meter cube. So it means that we will have a two state since one property is changed in such a way that the temperature inside the cylinder remains constant. So this is one of the important things in this equation. It implies that this process is conducted in a way that the temperature is constant. So this is we call as an isothermal process. But if it does not mention, normally for a piston cylinder device, we assume that the piston is frictionless or freely move. It normally we call as a isobaric process or constant pressure. But this question does mention it state the process have a constant temperature, so we need to use the isothermal relation for this kind of process. Okay, so now it asks you to find the work done. Okay, so I do not know whether the work is positive or negative, but since this is a compression, I target that you will get a negative answer for the work because this is a compression process. Okay, so now we need to identify what is the system state and also process here as usual. Okay, so I think I will make it this smaller. Okay, now I write here the system. Okay, this is a air inside piston cylinder device. So this is a closed system since no mass cross the boundary. And then what is the state? How many states? As I mentioned earlier, we will have two states because one of the volume is stated change, okay, which is volume. And then for the two state, it will be linked with a process. Okay, so what is the process? The process is isothermal, since it mentioned constant temperature, but it must be paired with another typical process, which is compression. So it mentioned about compress. Okay, now you can start to sketch your problems. Okay, I think I just used the previous sample. Okay, to copy the diagram. Okay, and then press here. Alright, so no heating here, no heating here. So this is still an air, but I think the volume will be reduced due to the compression. So I will change the position. Oops, sorry. Okay, so since this is a compression process, I will highlight with red color here. Compression is a work input. Okay, so the process here I state as isothermal pair with a compression. Alright, so now put your state 1 properties and state 2 properties as mentioned in the question. Okay, so what is the state 1? The state here contains 0.4 meter cube, that is the volume, and 100 kPa and 80 degrees Celsius. Okay, so I just copy here 0.4. V1 equals 0.4 meter cube, then 100 kPa, 80 degrees Celsius. This is your pressure and this is your temperature. Okay, at step 2, sorry, the air is now compressed to 0.1 meter cube, so that is the properties that is changed given in the equation 0.1. Okay, how about P2 and T2? So we do have T2 because this is a constant temperature, so it will equal to T1. And then about P2 does not mention. Okay, so but in this case I think the pressure will be increased due to the compression process. So look at the question. They ask you to find the work done during this process. Okay, so I think I put another page here. Okay, alright, so since this is ideal gas, we use ideal gas equation to find the work from state 1 to state 2, integration of P dV. I think we have derived for the isothermal, it will be equal to PV ln V2 over V1. So this one you can use either P1 V1, or you can also use P2 V2 ln V2 over V1. It doesn't matter. If you use P1, you need to use V1. If you use P2, you need to use V2, because this is based on the relation of PV over T equal to PV over T. So this is 2, 2, 2, 1. So for a constant temperature here, I cancel out T1 and also T2. So that's why we can use P1 V1 equal to P2 V2. Besides, also you can use replace this PV, sorry, just a stroke here, stroke black. Sorry, put no fill here. Okay, or P2 V2 also you can use just MRT1. This one you can use MRT2. Okay, all right, so now you need to use either equation that is at the least unknown. Okay, so if you want to use, let's say, P1 V1 ln V2 over V1, I think this is the most suitable because you have more variables here as compared to the second one here. Okay, so in this case I will try to use the value at state 1. Okay, and we look at what is the unknown that we left here. Okay, so W12 equal to P1 V1 ln V2 over V1. So now we look at what is the parameter that is not mentioned. So we do have here for P1. Do we have V1? Yes, V1. How about V2? V2 does not mention. So we have V1. So we left with a V2 here. Okay, we left with V2 here. Okay, we left with V2. We need to find V2 first, and then you can get W1 to. So in order to get a V2, oh sorry, V2 already mentioned here. Okay, so this is quite a straightforward question, and I think this is too easy to be solved. Okay, so we just put the value. P1 already mentioned 100 kPa. This is very straightforward. V1 is 0.4 meter cube. Then you put ln here. V2 is 0.1, 0.4 meter cube. Okay, so you get here ln you get here minus 55.45 kilojoule. So is that the only question it asks? Determine the work done. Okay, so yes, and our assumption of negative is correct. Okay, so this is very straightforward, and the only problem is you just memorize the formula or not for the isothermal work. Okay, that's all. Thank you.